This is going to be part 2 of the mechanical energy lesson. We're going to focus on non-isolated systems with this video. So once again, if you want a copy or a version of the copy of these notes, you can go to the class website. There's something there you can look at. Also, it wouldn't be a bad idea, again, to read Pearson Chapter 6 and see the other links involved. So the last video was about mechanical energy, about how all the energy that contribute to motion in a mechanical system is just the sum of the kinetic energies and gravitational potential energy, or just potential energies in general. Again, we're going to ignore our elastic potential energies. When you have an isolated system, the energy before is going to be equal to the energy afterwards, and you get to ignore all friction or compression or heat loss, thermodynamics in general, when you do your mechanical problems, because you assume that no energy is lost from the systems. When you have a non-isolated system, you have some kind of energy loss. Could be energy loss through friction, could be energy loss through air drag, could be energy loss through light, sound, any kind of deformation where it won't go back to its original shape. That energy cannot be reintroduced into the system. It is lost. It will not contribute to motion anymore. Once it's away from the system, it cannot be brought back in. It's not destroyed, it's just released into the atmosphere. And once it's in the atmosphere, you cannot get it back. So that just means that your mechanical energy before the scenario occurs is not going to be equal to the mechanical energy afterwards, which means when you have a change in energy, work is done. So remember, your change in energy would be your final minus your initial, or the after minus the before. And that technically means work is done. And remember, work is your overall net force acting on the system multiplied by the displacement in that system. So that can take on many different forms. Basically what that means, and I've crossed it off, but I left elastic potential energy on there. We're talking about the work energy theorem, which states that the work done on a system is equal to the sum of the changes in the potential and kinetic energies of the system. So in other words, you could be talking about how your overall change in kinetic energy when added to your overall change in gravitational potential energy is going to be equal to the work done. Sometimes that could be work which is energy lost, again, through heat, or it could be energy gained. Maybe there's chemical potential energy that we're not accounting for in the system. Like if you're pedaling your bike, every downstroke of your foot, you're adding energy to the motion of your bike, and that's going to cause you to speed up. So now that's chemical potential energy being introduced and being used as work, but we're not going to get into the chemical potential energy. My point is, forces can add energy to a system, forces can remove energy from a system. In both those cases, it is going to be considered a non-isolated system. So that could take on lots of different forms. If we look at your basic change in kinetic energy, we could just have a final kinetic energy minus your initial kinetic energy. Maybe the initial is 0, so you could just ignore this. Likewise, maybe the final was 0, so maybe you could have just ignored that. But it is really question specific. This is just kind of the generic equation to satisfy all questions. Last week when you watched your change in kinetic energy videos where you had a change in kinetic energy, maybe we went as far as just saying work is equal to just your change in kinetic energy. But now that we're talking about gravitational potential energy or just potential energies in general, we have to include that into our system. Sometimes it'll involve potential energy, sometimes it won't, sometimes it'll involve kinetic energy, sometimes it won't. It's really situation specific. Sometimes I like to rearrange it so that if I group all my final energies in one spot, I can subtract my initial energies in the other spot. So it's just a regrouping. So that's sometimes how I like to set them up, but some people prefer writing it out in this format. Another thing to recognize is if we're talking about work, we actually have an equation for work, and that is your parallel force multiplied by the displacement. Now, I didn't draw the vector arrows, but keep in mind these are vectors. So that means direction will matter in this case. So that means if your net force is acting in the opposite direction of motion as your displacement, then this will be negative. If it's acting in the same direction it's going to be positive. So positive work is done, energy is introduced into the system. If negative work is done, that means energy is lost in the system. And again, if this force is not acting parallel to this displacement, you'd have to bring in that multiply by cos theta. But I ignored that in this question just to keep it as simple as possible. So again, if you know the equation for your kinetic energies, you can take, this section right up here, your final kinetic energy minus your initial kinetic energy, and you can just write it like this if you would prefer. Likewise with your gravitational potential energy, if you kept it grouped in like this for your given questions, then you can just see it more as your overall change in your vertical position. So you can always write it in whichever format you want. There's lots of different ways to do the equations for your work energy theorem. And sometimes you might want to consider this equation here where you separate all of your final mechanical energies with your initial mechanical energies. And if you recognize if you're finding the difference, then you can just bring in the initial mechanical energy to the left-hand side of the equation, and then you just create an addition, all right? And that being your total of your initial mechanical energies added to the work done should be equal to the total of your final mechanical energy. So this is a different way of looking at it. In fact, this is essentially your first law of thermodynamics if you want to go back through your notes from last year, except this might have been called Q or H, and this might have been called Q or H, but it's the same idea. So that's really what we're doing right now. So I've got one problem, and this will probably take me 10 minutes to go through. I'll try to go through as quickly as possible because you can always pause this video if you need a break. It's not the hardest question out there, but it's a different question. So you got 10-kilogram block that's released from point A. So there's point A, and the slope is frictionless except for the segment between B and C, and it has a coefficient of kinetic friction of 0.3. So that means when this is released from rest, it's going to slide down here and it's going to hit B. And well, if this is a rough surface, it's going to slow down between B and C. So there's three parts to this. Question one, what is the speed at point B? Question two, what is the energy at point C? And part three, what is the speed at part C? So this question has two main parts. You have your isolated portion between A and B where no energy is lost because it says nothing about, well, it does say that the ramp itself, the slope is frictionless. So that's our way of indicating that no energy is lost between A and B. Or at the very least, the friction is so small that it's pretty much negligible. So you can always interpret it that way if you want to think about realistic physics. And then air drag, obviously this is not going to be going fast enough. So air drag is just something you can ignore for the most part. And then between B and C, the second part, that's going to be a non-isolated system. So our energies will not be equal. We're going to have loss of energy, so work is going to be done. Negative work in this case, energy is going to be lost, so it's going to be removed. So back to part A, question one, the speed at point B. Since we start at the very top, I know that I have gravitational potential energy. It says the block was released. So whenever I hear the word released, my first thought is, oh, my initial velocity is 0. So there's no kinetic energy to start with. So that means all I have for mechanical energy at part A is gravitational potential energy. By the time it gets to part B, right, down here, I'm on the ground, so I have no height. Therefore, I have no gravitational potential energy. So all I have for mechanical energy at part B is kinetic energy. And so I can just create this cute little equation just like that. Gravitational potential energy is going to be equal to your kinetic energy. Moving forward, just going to slide it off to the side. Oh, went a little fast. If I put in the equation for my gravitational potential energy, I can see that I have my kinetic energy, both have mass when I put both their equations in. Now, normally I would just cancel off those masses and just solve for my velocity, but I know in part 2 and 3, it might be handy to know what my initial energy was. So for that reason, I did not. I just went straight ahead and wrote down the equation. So mgh for part A, and then plugged in those numbers. So otherwise, if I was done and I didn't have to bother with part 2 and 3, I would have just canceled the masses off and brought the 2 over and then taken the square root. But there's more parts to this problem. And often when there's multiple parts to your guys' work problems, sometimes it's very handy just to find the energy at one point, and then you might be able to use that at another point and save yourself some time. So plug in those numbers. 10 times 9.81 times 3 should give you about 294.3. I kept the full value. Should just have 3 sig figs according to the significant figures that I see here. So you should have just shy of 300 joules at part A, which means you should have 300 joules by the time it gets to point B. Since I'm looking for my speed at point B, I'll bring that equation down. I have the same mass, so I'll just take half that mass, divide it out, so divide both sides by 5 kilograms, and then just take the square root of my both sides, and you should end up with just a little less than 8 meters per second as the speed at part B. So 100% of the energy has been converted from gravitational potential energy, and now we just have kinetic energy. So all of this energy stored up in its height has been converted to the energy of motion, and specifically traveling about 7.67 meters per second. So that was part 1, the speed at point B. Part 2 is asking for the energy at point C. So how much energy does it have once it goes through this rough patch? So while it's traveling from point B to point C, it's going to be losing energy, so therefore it is a non-isolated system. So the energy at B is not going to be equal to the energy at C. So knowing that, I know work is going to be done. So my work is going to be equal to my change in energy from point C to point B, which means C would be considered my final location. So that would be my final energy. So whenever I find a change in anything, it's always final minus initial. So that's why I know I should set it up so that I have my energy, mechanical energy at point C, subtract my mechanical energy at point B, because this is the final location. This is the initial location of our current spot. So if you set that up, life should be good. Moving forward, my work equation says I need a parallel force multiplied by a displacement. Well, I've got the displacement in the diagram. It travels 6 meters to the right. If I'm reading this diagram correctly, it's traveling 6 meters to the right. So that one is figured out. It's my parallel acting force that I don't know. It wasn't given in the question, but it was given as kinetic friction. So I've got a coefficient of kinetic friction value. So that's not a force, but it's a value that's used to calculate friction. So that means I need to, oops, I think I clicked twice, no, once. That means I have to recognize that, well, my block is moving from B to C, so I drew it on there, which means I need to have a free body diagram. So I drew a free body diagram, so there it is, between B and C. I know that while it's sliding from B to C, there is no force pushing it to the right. There is 2 vertical forces, the normal and its weight, but they will cancel each other out, so we don't have to worry about those. It's on a flat surface, so again, they will cancel out, so just ignore them. Draw them in, but otherwise ignore them. The only force that's acting is going to be friction. Okay, friction is going to be acting in the opposite direction of motion, but as far as its magnitude is concerned, remember friction is just your coefficient multiplied by the normal, and when there's only 2 vertical forces, your normal should be equal to your weight. So you can just replace the normal with your weight, and you have an equation for the magnitude of friction to be your coefficient times the mass times the gravitational field or acceleration of gravity. So back over here in your actual equation, you can replace your parallel acting force with that of friction. Now remember, we are using vectors, right? So these 2 guys are vectors. Your displacement is traveling to the right. Friction is moving to the left. So that means when I plug this coefficient times mass times gravity over here, it should be a negative value. Right, so there's my negative. I got rid of the vector symbols here. I've now accounted for both their directions. They were in opposite directions. So I threw in the negative, and now I can actually proceed with the rest of this question. I also know that my mechanical energy at part B, I've already figured that out. That was down here. So my mechanical energy at point A was equal to my mechanical energy at point B. And once I plugged in the numbers for point A, part A, I had just slightly less than 300 joules. So I actually know my mechanical energy at point B. So I'm going to put that into the equation. I'm going to plug all my numbers in. My coefficient was 0.3, my mass was 10 kilograms, my acceleration of gravity is 9.81, and my distance between B and C should be 6 meters. Once I plug all those numbers through my calculator, I get something around 176.6. I think I rounded that number up. I don't remember at this point, but it wasn't a perfect number. Bringing in my energy from my mechanical energy from my right-hand side there, back to the left. So I'd have to add when I brought that thing over. So that's why I'm adding the 294.3. And then when I combine those together, I get, I believe, slightly less than 118. It's about 117.7-ish as my mechanical energy at point C. So that's what my calculator said. I'm just going to round that up to 118 for this video's purpose. So part 1 is done. Part 2 is done. That's how much energy it has left. You can see that we were around 300 joules. Now we're a lot closer to 100 joules. So we've lost almost 200 joules of energy. Well, almost. So about 180 joules almost. So now we just want to know what is the speed of the block once it passes point C. So it looks like on the diagram that we no longer have friction afterwards, just a nice flat black line on the diagram. So that looks just like the same line that we had before. So it's pretty much implied that we have no friction anymore. So how fast is it going once it passes part C? So if I move everything, make it smaller so I have more room, I know that my mechanical energy at part C is going to be equal to my kinetic energy at part C. All right, so that's a K, apparently. That's what I have left. So I'm not trying to figure out a part D or a part E or whatnot. Just I now have a block. It's going to be sliding in that direction indefinitely as far as we're concerned. So all I have to do at this point is figure out how fast it's going. Plugging in what I know, I had about 117.7 joules. I know that it's kinetic energy from this point on because it's not going to doesn't look like it's going to be changing its elevation. So all I have for mechanical energy is kinetic energy, and I can just plug numbers through. 1/2 mv squared. Well, 1/2 10 kilograms is 5. So if I divide both sides by 5 kilograms, I can cancel off that mass, get around 23.5 meters squared per second square. If you take the square root of that, you should be around just a little shy of 5 meters per second. So originally, when it got to part B, transferred all of its gravitational potential energy into kinetic energy. Specifically, it's going 7.67 meters per second at part B. And then it's going to lose energy as it goes from point B to point C. So that means work is done. You have a non-isolated system here. So when work is done, it's going to, in this case, it's going to lose energy. Some cases it might gain energy, but in this case, it's definitely losing energy. And it lost a little bit of speed because of that. So friction is going to cause things to slow down. So I hope that made sense. Try some of the problems. They vary in difficulty. You should be able to complete all the problems now from the workbook. Do ignore the elastic spring potential problems. You don't need to do those for this course, thanks to COVID. So give it a try and email me if you have questions. I'll post an assignment for marks probably Wednesday night or Thursday morning for you guys to work on. And you get that to me as soon as you can. All right, we'll stop it here.